All right, this is 6.1 example one, and we're going to look at, basically what is an identity. Now, an identity is when for any value of the angle, except for non-permissible values, we get the same numerical value on the left-hand side and the right-hand side. So we're going to determine kind of how to verify this. But first, A asks us for the non-permissible values. To do that, you have to make sure that you rewrite the reciprocals as their primaries. So that secant theta is going to become 1 over cos theta. And then on the right-hand side, this can get a little bit ugly, but tan theta, I'm going to rewrite as sine theta over cos theta, and that's embedded within the larger fraction that has sine theta as a denominator. So basically what I'm going to do now is I'm going to take any denominator in the equation and say that that can't be 0. So cos theta cannot be equal to 0. That's from this location and this location. And sine theta cannot be equal to 0, and that is just from this denominator right there. Now, in order to solve these, this is beneficial to know your unit circle. Cos theta is equal to 0 anywhere the x-coordinate is equal to 0. So this tells me, and I'll do degrees here, that theta cannot be equal to 90 degrees or 270 degrees, and certainly there's a lot more numbers than that. The way that we describe all of them is with that general solution that theta cannot be equal to 90 degrees plus 180 degrees n times, where n is any integer. Right, that describes every single non-permissible value for that cos theta. Sine theta gets done very similarly. If sine theta can't be equal to 0, that's when the y value is 0, which is 0 degrees, 180 degrees. I'm going to put 360 on there. That would, again, continue in both directions. Very similarly to cosine, that means that I could write this as theta cannot be equal to 0 degrees plus 180 degrees n. Now, it's worth mentioning that these are non-permissible values for the entire question, and annoyingly, we can actually combine those. Keep in mind that this would have 90, 270, 450, and all those numbers along the way. We are basically going to catch every single multiple of 90 degrees. So we could say that theta cannot be equal to 90 degrees n, where n is an integer. Now, the reason that is because we are covering, when the x-coordinate is 0 and the y-coordinate is 0 on the unit circle. That's going to happen at every quadrantal angle, so we get every 90-degree multiple, including, remember that 0 is an integer. So 90 degrees is included in that as well. Okay, that is just doing non-permissible values. What the remainder of the question asks us to do, and really what is important is verification is a really important concept that we're going to do again and again and again. To verify basically means to take a value of the variable and plug it into the left-hand side and the right-hand side separately. So in order to do that, I'm going to take that value. We'll do degrees first, the value of 60 degrees. So we have 1 over the cos of 60 degrees, which we'll evaluate in a second. And we want to check if that's equal to, and I'm going to write that in as I did above because I think it's a little bit easier. We're going to have the sine of 60 degrees divided by the cos of 60 degrees all over the sine of 60 degrees, which can get a little bit ugly for sure. What we're going to do now is use our unit circle knowledge and start plugging in some of those values. So the cos of 60 degrees, if we look at the point at 60 on our unit circle, the coordinate is 1/2 comma root 3 over 2. Cos is the x value, so this is going to be 1 divided by 1/2, which is 2. So that's what my left-hand side is equal to. I'm hoping I can manipulate the right-hand side and have it be the same expression. But again, who knows? If it doesn't work, then this is not verified and it's not an identity. So on the right-hand side, the sine of 60 is root 3 over 2. The cos of 60 is 1/2, and that's divided by root 3 over 2. Now, this is a tricky concept, but I'm going to take the numerator, which is root 3 over 2 divided by 1/2, and I'm going to multiply it by the reciprocal of the denominator. Now, I'm going to write this a little bit weird. I'm going to write that as 1 over root 3 over 2 because these would cancel. And I'm left with 1 divided by 1/2, which is equal to 2. Now, because the left-hand side and the right-hand side share the value, we would consider that to be verified. At 60 degrees, we get the exact same thing on either side of this identity. All right, we do also have to check when theta is equal to pi over 4. Hopefully, you're on the ball with this and you remember that means I need to think about radians, but we're going to do the same concept. We're going to look at the left-hand side and we're going to look at the right-hand side. Very important that when we verify, we do not manipulate, other than maybe some of those proven identities like I did above. I'm actually going to go back to the original here, So this is going to be the secant of pi over 4. And then on the right-hand side, I would have the tan of pi over 4 divided by the sine of pi over 4. Now, right away, nobody memorizes the secants of the angles on the unit circle. So I just wanted to talk about when you have the secant of pi over 4, you need to remember that it's 1 over the cos of pi over 4. So this is 1 divided by root 2 over 2, which is root 2, oops, sorry, not root 2. Multiplying by the reciprocal would give me 2 over root 2. We know the pain of our textbook. They will rationalize that. They'll write it, or at least the middle step is 2 root 2 over 2. So root 2 is my left-hand side. Now, one of the reasons I wrote tan in there is pi over 4 has the same x and y coordinate. So the tan of pi over 4 is 1. And the sine of pi over 4 is root 2 over 2, which is 1 multiplied by 2 over root 2. When I rationalize that, I'm sure we can see what's happening here. I get 2 root 2 over 2, or just root 2. And again, that's verified to be true. One of the tricky things about verification is you have to be really comfortable with the mode on your calculator, because you are going to have to switch, right? If you look at, section B for this question, part of that was done in degrees and part of that was done in radians. The last part of this is calculator work, and it wants us to show that their identities graphically. And really what that means is that their graphs have to look the same. So what I've done is I've put in y1 as the left-hand side. Again, no secant button, so I have to use cos x. I can't, 1 over cos x, I should say. The right-hand side can be written exactly as is. Very, very important you close the bracket after your trig identities, just a good habit to get into. Now, I am going to go to zoom trig, so that's the zoom button, number 7, but it wants us to verify this. Sorry, we're just going to stop that graph with the on button. Go to our window, and they only want us to look at this between negative 360 and positive 360. Now, what I've done on my calculator is I've told it that, to graph 1 over cos x in blue and then graph tan x over sine x in red. If this is an identity, the red graph should go or look exactly the same as the blue graph. Now, one thing that's very important is there are non-permissible values on this graph. Some of them result in asymptotes, some of them don't. When you talk about proving an identity, it is only for permissible values. So non-permissible values don't make an identity incorrect. We talk about them as almost exceptions to whether or not the identity is true or not. So when I do hit graph in blue, this is the graph of secant x. A little bit weird for sure. It has these asymptotes, and we should recognize where they are. They're where cos x is equal to 0, and then it's going to graph the right-hand side. And I hope you can see that the red graph is perfectly overlapping the blue graph, except for this little gap right here. That is where the red graph has something called, well, we learned this, that's a point of discontinuity. That's where on the red function, tan x over sine x, I would see a point that kind of looks like it should be non-permissible, and it is, but it actually results in a 0 over 0 situation, when in this case, it's a point of discontinuity, not an asymptote. But the end result of this is that these two graphs look exactly the same. So that proves that the identity is true. All right, we're going to keep going for example number 2.